So now we will get started. Um, Today I'm going to introduce my recent research, which is about we propose the ideal data for efficient deep learning. And my name is Peng, and I'm from the Westlake University this lab. And is happy to share my research here today. So let's start from some background of deep learning. As we all know that the model ability will emerge as its capacity and the training data increase. And for two examples, in the left of this figure, we can see the recent popular the video generation model called Sora. It can generate high quality videos, but it's based on a huge model and training data. And in the right part, we is also a popular data generation model, the GPT-4. I think all of maybe all of you could know these two models. However, we are facing the key changes that the need for human annotation of vast amounts of data will require significant social resources. For example, for the imagined 1,000 dataset, we need many human workers to give it the labels or targets. So it will consume huge amount of social resources. Fortunately, we have a solution called self-supervised learning. It can effectively addresses the unlabeled data by self-generating the labels. As you can see in this figure, I have shown an example of self-supervised learning called BYOL. It's a widely used self-supervised learning method. You can see that in BYOL, we use a momentum encoder to generate the targets, the pursuit targets for the given images. And we use the encoder and the predictor to predict this self-generated targets. And we use the loss to perform the gradient descent and update our model. However, there is some issues in existing solution. That is, self-supervised learning is less efficient than human-supervised learning due to the low quality of self-generating labels. As you can see in this figure, when we use the BYOL to train a model, the accuracy will increase but slowly. While when we use the human-supervised learning, the accuracy will increase more faster. Sorry. So in this paper, we want to accelerate the training of deep learning methods or deep neural networks from the data efficiency perspective. So let's start from a simple case study. The first question is, how can we efficiently train a 3-layer neural network to classify a bimodal Gaussian mixture distribution? And in this paper, we use the G to denote this distribution, and it consists of two parts. The samples part denoted as the GX, and the targets part denoted as the GY. So we also visualize this distribution. And you can see in this figure, there are two classes of the Gaussian distribution, the red and the blue one. And the color bar here is used for labeling their target value. That's 0 and 1 for this figure. Now, let's shift our attention to using the refined samples. As we just say, we want to refine the data set into another one, and we want to increase the training efficiency. So at first, we will use the original targets. That means we will fix the targets and changing the samples here. And we find that when we reducing the variance of the samples, which is denoted as G prime X, and the variance is denoted as sigma. When we reducing this variance, we will enhance the training efficiency. For example, in the figure A, we can see that if we use the sigma that equals to 0.1, the training dynamic will be very smooth. The trajectory here will be smooth. And if we increase the variance of the samples, we can see that we will introduce more noise and the trajectories are not that smooth. And in the figure B, we evaluate the gx prime with different sigma values. And you can see that if we use the smallest one, that's 0.1 sigma value, the validation loss will decrease very fast. And if we use that equals to 1.0, the validation loss will decrease very slow. So in the figure C, we also visualize the optimal gx prime. So you can see that here we use the sigma equals to 0.1, and it looks like that the variance is small. So the target is still remains zeros and ones, but the samples comes to the like their mean of each distribution. In the second experiment, we focus on utilizing the refined targets denoted as G prime Y. And we enhancing the intensity of relabeling via a pre-trained model denoted as rho. And we try to use this term to improve the training efficiency. And you can see in the figure A, if we use the when the rho equals to 1.0, that means all the labels is relabeled using the pre-trained model. In this case, the training trajectory is very smooth, and it will approach the global minima very fast. And in the figure B, we can also see that if we use the biggest rho value, which is 1.0, the validation loss will decrease very fast than the other values. And we also visualize this optimal G prime Y. That's where we use the rho equals to 1.0. And I have just told that the color bar here is used for marking their Y values, their target values. So here the target can is not the hard ones. It comes to be the soft targets. So so you can see here the colors will change smoothly. Now let's have a conclusion of our case study. As a conclusion, we can say that we should balance the diversity of the samples and the targets to maximize the training efficiency. For example, in our case, the original when training over the original data is not that efficient, but we can fix the targets and reduce the variance of the samples. It means that we use the hard targets, the hard labels, which is not that diverse. So we need to use the corresponding in diverse. Sorry, I mean the collapsed samples to match the targets. And when we use the fixed samples, it's diverse. The original samples is diverse. We should utilize the diverse targets to match it. So for a conclusion, we can say that we should balance the diversity of between samples and their targets. And by the way, we have also provided the theoretical results for this phenomenon. And there are more theoretical results that we demonstrate that altering the samples can adversely affect the generalization of the models trained on real world data. It means that, as we just said, we can alter the samples or targets, but we provide more theoretical results which shows that we cannot alter the samples because it may hurt the generalization ability. So now there only remains one solution. We should maximize the training efficiency by providing diverse and accurate targets for the diverse samples. So the question, sorry, this insight is also aligned with our previous findings, where we find that when we use the human labeled data, the training efficiency will be larger than that of the unlabeled data. This insight is aligned with that theoretical insights, but however, the question is, how can we generate such targets for unlabeled samples without the human annotation? So now I'm going to introduce our proposed method, which is called RELA. It's an economical approach to generate efficient data. So let's look at these two figures. In the right part of the figure, we can see that we first download any model, any freely available model from the internet, and we use this model as the prior model. And we use this prior model to do an inference on the unlabeled data, and after this inference, it will generate the corresponding representations or the features of the data, and we just randomly select a subset of this new data as the display data during each training epoch. And in the right part of this figure, we can see that our proposed RELA will define a new joint loss function, and it shows here. It introduces an additional cosine similarity loss function between the psi x and our the learner model. So so this is the key idea of our method, and so I'm going to explain why we call it economical. You know that when we just if we want to use human workers to generate the targets, it will consume much social resources. But when we download a model and we do an inference stage using this model over the unlabeled data, it could be very cheap. So that's why we call it economical. And now I'm going to introduce the intuition behind our RELA. Before it, I will introduce that we use a dynamic coefficient, that's lambda, to balance the two loss terms in RELA during the training, denoted as this equation. So I'm going to introduce two things. The first is why we use this coefficient, and the second thing is that why this coefficient and the RELA loss function works. But I can only intuitively explain this equation. For example, in this figure, you can see that if we randomly initialize a model, it should be it should be located on the edge of the representation space and would be far from the target model. So if we directly use the original training algorithm, it will approach the target slowly. But for our RELA, when we introduce the dynamic coefficient, the training stage can be divided into two stages. In the first stage, or the early stage, the lambda is close to 1. So the 1 minus lambda is close to 0. And in the RELA loss function, there will only one loss term. The first one works. And if we just look at the first loss term, it could be considering as that we use our learner model to approaching the labeled model, the psi x, and we have and we show that when we use this term, the learning will be faster. But the question is, the level model, which is just randomly downloaded from the internet, could not be our target model. So the first term can only bring our learner model close to the target model first, but it cannot be the exact one. So that's why we need the dynamic coefficient, and in the later stage of the training, we will let the coefficient lambda close to 0, and 1 minus 0 term will be close to 1, and it means that this loss function will in fact remains the second term, the L algorithm. It's the original loss function, like the self-supervised learning loss term, and it will drive the model from the facili regions come to the target model. So it's okay if you don't understand what I introduced before this page. If you understand this page, only this page, the key idea of our RELA can be understood, and a more intuitive, a further intuitive understanding is that RELA can be considered as a learning includes two stages. The first stage aims to learning efficiently, and the second stage drives the model to the target model. So it works like the human learning. It also works like the human learning stage. For example, imagine that for a baby is it could be considered as the randomly initialized neural network. In the first stage, we need to let some teachers to teach it the knowledge, and it will let the baby to approach the teacher, but that's not all, which means that if the baby is not all for the baby to become the teacher, it should become more stronger. So in the second stage, the baby will try to work like the self-supervised learning. He or she will read books or papers by itself and learn by himself. So that's the very high level intuition behind our method. But of course, there is no corresponding theoretical results to support this intuition. But I think it's somehow interesting. So now let's come to the experiment part of this work. So the first is that our RELA can significantly accelerate the training stage of any self-supervised learning. Here we use the BYOL as the example. So you know that our RELA necessitates pre-trained or pre-downloaded models as the prior model to generate the efficient data or display the data. So here we use 6 downloaded models with different power. From the first one is a random initialized model, and the last is the very powerful CLIP. And the other four the representation ability can be considered as the increasing. For example, the second one is the CEFR-10 trained model, and the third one is the CEFR-100 trained model, and the tiny ImagiNet trained one, and the ImagiNet 1000 trained one. So there are six pre-downloaded models used to combine with our RELA and accelerate the BYOL. We also provide the results when just using the original BYOL with different partition of the original dataset. And the BYOL star is that we use the full dataset, the 100% dataset, to train the BYOL and get the corresponding result. So, for example, sometimes we may use only 10% of the full dataset can outperform the full data training accuracy. For example, when we use the CLIP to generate the efficient data through our RELA, the final training accuracy is about 83.2, but the full data training accuracy is only 82.8. So we can say that RELA can sometimes help the self-supervised learning method accelerate 10 more times, and but it will be hard for the large-scale dataset. For example, when we use the dataset ImagiNet 1000, we can even we use the most powerful prior model CLIP to generate the efficient data, and even we use 20% of the dataset for the training, we can only achieve the 7.7 accurate top one accuracy, but the full data training accuracy is about 62. So I think the how to say, I think the accelerating is associated with the dataset what we use, and the prior model what we use. So a general conclusion is that when we use more powerful prior model, the increase of the training efficiency will be more than the case where we use the less powerful prior model. So the second experiment is that we evaluate our RELA across different self-supervised learning methods. As we claim that we want to use our RELA to accelerate any self-supervised learning method, so it's not enough to only conduct experiments on the BYOL. We have collected 7 more self-supervised learning methods to comply with our RELA, and we report the corresponding experimental results on the dataset of several Peng and tiny ManGNet. And here we only use two kind of prior models, as we just say that the increase of the training efficiency is associated with the representation ability of the prior model. Here we only select two prior model that's as the representatives. The first is the random initialized model, and the second one is the CLIP model. So I think our conclusion is still unchanged. That when we use a more powerful prior model CLIP, the increase of the training efficiency will be better than that when we're using the random initialized one. However, we can also find that for any self-supervised learning method we utilized, the random initialized model can increase the training efficiency of these methods. I think it's interesting because it's easy to understand when we utilize the CLIP to accelerate the training procedure, because that CLIP is trained over a large amount of data and is very powerful. So maybe our method can introduce some knowledge from the CLIP into the trained model. But the random initialized model, it hasn't been trained over any data. So it cannot introduce any knowledge into the trained model, but it also increased the accuracy of the trained model when we combined this with any self-supervised learning method. So I think our RELA, for an conjecture or the conjecture explanation, maybe that our RELA works like an implicit regularization term that helps this method achieve better performance. So that's all my presentation. Thank you for your listening, and sorry for my poor English. It's not that smooth. Hello?